So alcohols is our theme today. Just keep highlighting. So if you ever see the term family, what family is it? You know, referring to like anes, enes, ines, cycloanes, cycloenes, and now we're into alcohols. Okay, they're hydrocarbon derivatives. Anytime you have something other than C and H, it's referred to as a derivative. And we have this hydroxyl group. As we work our way through the rest of the families in this course, they're going to have a unique set of atoms that makes, that creates a certain family. So the hydroxyl group is the functional group that makes something an alcohol. So I have a little dash here. That's a dash meaning that it's connected. That's a covalent bond, 2 electrons, that's going to be connected to something. Okay? So if you have an OH connected to a carbon, that makes it a hydroxyl group and makes it an alcohol. Please make sure you keep that OH totally separate in your mind from hydroxide that you're quite used to. Okay? They're not the same. Don't confuse them. This is an ion that makes a solution basic. This is the hydroxyl functional group. This is not negative. This is going to covalent bond to something, and you'll see that all through the lesson today. I'll throw up a quick example. So the simplest alcohol, which would be methanol, would be that guy. So there's the hydroxyl group connected to a carbon, which is, again, very different than this OH being connected to a metal and an ionic interaction. Naming, starting point to naming is fairly similar. We want to get started with what is the alkane stem that's making up the alcohol. We're going to do something different for the first time. We're going to drop that last E in the alkane name and add OL. Okay? So when you see this OL, that quickly tells you it's the alcohol family. A number may be required to tell us where that OH group is. So we have all the same numbering rules in terms of if there's more than one option, you have to put it in. If there's only one option, you don't. In this example, which is methanol, there's only one carbon for the OH to go on, so no number would be required. Okay. I'll do a couple larger examples. So I'm going to do 3 carbons with an OH at one of the ends. Okay. So find the longest chain. Like with enes, the OH would have to be in the longest chain. So if there's a few ways to go, make sure you include the OH regardless in that chain. Okay. There's no branches here. We have 3 carbons, prop. We're going to use the full alkane name, propane. Drop the last E, add OL, and then think of whether we need a number to denote where the OH is. And in this case, we definitely need one. The OH is in the 1 position, but it could have been in the middle. It could have been in the 2 position. So you have to tell the reader that it's in the 1 position. So propan 1-ol. The line structure, we now have a letter other than C and H, so we have to draw those in explicitly. I'll start with the pro part. 1, 2, 3, and a lift. So there's my stem. And then I have an OH at the end. So I'm going to put what would look like a methyl group, but I'm going to put an O at the end. that says, okay, there's no carbon here anymore, there's an oxygen there. Okay? And then you have to show the H. We only drop H's that are bonded to carbons. Okay? Any O's, or sorry, any H's bonded to something else, and you're only going to see oxygen in this course, you have to write it in. Which makes sense. Dropping this H would be very confusing. You may not be sure what's there. Okay? So that's the correct line structure. One more example, and then we'll move on a little bit in complexity. We'll put 2 hydroxyl groups in on the next slide. So I'm 4 carbons long, a OH on the second carbon from the right, and then a methyl group next to it. First part would be to find the longest chain. There is a branch here, so I have multiple directions, but this piece has the OH. So I'm going to include this piece no matter what the count tells me. This has to be part of the stem. 1, 2, 3, 4 if I go up, 1, 2, 3, 4 if I go across, so it doesn't matter. I get a tie of 4, including the hydroxyl group. And I end up with a methyl group. Now, the first thing I have to do, the most important part of this molecule, is the fact it's in the alcohol family. So I'm going to number to the alcohol first. I'm not going to minimize the number to the first thing. It's the alcohol that matters. You do the exact same thing if you have a double bond. You don't care about alkyl groups. You get to that double bond first. So this side is the side that gets me to the alcohol, the hydroxyl group first. So I'm going to start there. Okay? Even if I had a chlorine atom right there in the 1 position, I have to go from this side. But something out here would actually be in the 4 position. So that is bute. I need some room here to put in that alkyl group, so I'm going to move over a little bit. Bute, I need to say butane, drop the E, the hydroxyl groups in the 2 positions. Okay, so I just haven't dealt with that methyl group, so it's 1, 2, 3 over, so we have a 3-methyl-butane 2-ol. That is one word. There are no spaces in the name so far. Next, you're going to have to know how to name what if there's 2 hydroxyl groups in the same molecule. We'll cover that. So alcohols with more than 1 hydroxyl, same rules, except I find this first rule silly. I wouldn't, if I was the ruler making the rules, I wouldn't put this in. You can't drop the E. You've got to remember to leave that last E in. And that's where I find it weird, but doesn't matter. We're all following the rules. Okay. More than 1 number is often required to tell us the position of those 2 or 3 or 4 hydroxyl groups. So same numbering rules as before. Put numbers in unless there's only 1 possibility. Okay. You're going to add a prefix in front of the OL. If there's 2 hydroxyl groups, di, 3, tri, 4 would be tetra. Okay. I never personally assess beyond 3, a triol. Okay. So I'm going to draw propane 1, 2, 3 triol. And I'm going to go right to a line structure. It's the first time I'm going to do this, but I want you to, get used to doing that or being able to do that. I'm going to get out the stem. So prop, 1, 2, 3. And I see the tri, so there's 3 different hydroxyl groups in the 1 position, the 2 position, and the 3 position. So at the very beginning, I'm going to put a bend and put an OH. Please make sure you don't do this. The H doesn't connect to the chain. It's the O that connects. So that is not correct. It's the O that connects to the chain, then the H. Something, if you're in a rush, it's easy to do, but it's a bad habit. OH, and then OH. My 1, my 2, my 3. Okay. Now, have I made an error? Did I need those numbers? Is that correct? Or is that incorrect name because those numbers should go away? I'm just going to pause for a little bit more. I'll get your opinion, but so you're thinking, is there any other number? I spread them out. What do you think, Gabrielle? Yeah, perfect. This end has, there's a carbon here with another bond to a carbon, and there's 3 other spaces to bond. You could have a propane 1-1-1 triol. So there's lots of possibilities. You could have a 1-1-2. You could have a 1-1-3. Lots of options. You absolutely need the numbers in this case. I've not made an error. Okay. My last diol example, ethane 1,2 diol. I'll do the line structure again. Now, I included this. Part of any science course is connecting the science you're learning to chemicals in everyday life. This is what you use in your car. If you go to Canadian Tire, you buy ethylene glycol, antifreeze for your car. Most cars are 50% the diol and 50% water. Okay. For some reason, my Toyota is 55% this, 45% water. Okay. That's what the manual says for colder climates. Okay. So a highly toxic chemical, you certainly do not want to drink antifreeze, but that's where you can easily buy it. So ethane, 2 carbons, 1, 2, lift. So we got 2 ends of a line segment. That's my 2 carbons. Now, as a student, you have to realize, there's, several missing H's here. A common test question might be, what's the molecular formula of this, to see whether you understand where the missing H's are and where the missing C's are. You should be expecting questions like that. Okay. Any concerns about diols before we keep going? This is where once students get a good understanding of those first few lessons, there's a lot of repetition. We're building on that same fundamentals of STEM, which I had a question this morning. Parent is another name for STEM. If you ever see what's the parent here is S. I just call it STEM, but they're synonyms. A couple more slides. One is just to pure memorize. There are certain large molecules that have been given names because they're so common and we use them over and over again. One of them is phenol. It's an alcohol, but it's made out of a benzene ring. So there's my 6-membered ring. It's not benzene yet. That's cyclohexane. I'm going to put the circle in, which is one of several ways that we can convey that a ring is a benzene ring. And then at any point is a OH. Okay? It'd be in the 1 position no matter where it comes off. And that is phenol. And you could see derivations of this. You could have a 2-methyl phenol if you're 1 away. And one more slide on alcohols before we'll move into carboxylic acids. we're going to talk about primary, secondary, and tertiary alcohols. So there's going to be 4 total rows, 1, 2, and then the secondary and tertiary row. I'm going to draw a structure here, so I would give yourself a couple lines. Don't just do 1 line on your piece of paper as you lay out this table. Maybe 3 or 4 lines. So we have primary alcohols. I'll draw an example in a bit. Number of carbons connected to the COH is going to be 1 in a primary alcohol. So I'll let you set this up. Now I'm going to color code this. You don't have to, but I'm going to make the COH one color. In any primary alcohol, there is only 1 carbon connected to the COH, and I've made it red, COH. Okay? This carbon has 3 bonds left. There's only 1 carbon connected. The other 2 bonds need to be H's in primary alcohols. Now this carbon could be 1, it could be a row of 100, it doesn't matter. It's only of the 3 options connected to this red carbon, how many of those are carbons? This length is irrelevant. I'm going to draw 1 because that's the easiest to draw. It's a waste of my time to do 4 of these. It doesn't help my teaching. Okay, so I'm doing 1, but it doesn't have to be 1. The blue can be any length. Okay. Now unfortunately we don't take the next step with this. The next step you'll do in first-year university organic chemistry, which is study reactions in more detail. In primary alcohols, this carbon is part of a very polar CO bond, and this carbon can be attacked in reactions. And these H's are really small. How many subatomic particles are in an hydrogen? Depending on your perspective, you get answered a couple ways. So I heard 1, there's 1 proton, and then it's sharing 2 electrons. So even though I may draw an oxygen here, but oxygen has a whole bunch of protons, electrons, it's way bigger. This is teeny tiny, and this carbon can be easily attacked. Primary alcohols react really fast. But unfortunately, you're not going to learn that from me, but that's why you need to know this. So when you go to organic chemistry, you can study rates of reaction and study alcohols, the type of reactions. Okay. Secondary alcohols, we now have 2 of the 3 potential connections are carbons. We're starting to block up that red carbon. And these react a lot slower. Last, tertiary alcohols. There's the COH. There's 3 more bonds around that carbon, and there's a carbon in all 3 of those spots of varying lengths. The lengths are irrelevant. I'm putting methyls because they're the easiest to draw in limited space. tertiary alcohols react totally different from primary alcohols. They don't do the same steps at all. Even though they're both alcohols, there's no analogy to their mechanism of how they react. Okay? But that's first year university. But you need to understand this in order to do that first year university course or second year organic, depending on your institution. Okay? So if you get an alcohol, you need to be able to understand whether it's primary, secondary, tertiary. So that's it for alcohols. I'm just going to flip back and apply that to a few examples we did, and then we'll move on to acids. So if we look at propane 1-ol, is that primary, secondary, tertiary? So this is a primary one. There's the COH, and that carbon has one connection to another carbon. The other two are H's. So that's the carbon you're looking at. So that one is primary. This second one, 3-methylbutane 2-ol, okay, the carbon we need to focus on, there's the C to the O to the H, and that carbon is connected to 2 other carbons. This carbon has 1, 2, the third option is an H, so that's a secondary alcohol. Carboxylic acids. So we're on to another functional group that goes with this family. These are organic acids that contain a carboxyl functional group. We saw these all through Chem 20. I really wish we learned this before we did Chem 20, but that's not the order. The carboxyl functional group has a carbon that's double bonded to an O, and then single bonded to an OH. And this arrangement creates a circumstance where that H pops off fairly easily. Not 100%, they're all weak acids, but a relatively large amount of that H can come off. The reason it can come off is when this comes off, you get a buildup of, you get an extra electron here, but that extra electron could sit here or could sit there. It's got two identical symmetric options to where it can be located. So half the electron density sits here and half the electron density sits there. It spreads itself out and makes it really stable, which makes it very stable for that H to come off. H's don't normally come off hydrocarbons. It's quite rare. But this is one of the few circumstances that it is possible for an H to come off. Hopefully that's familiar from last year a little bit. We saw lots of these. Okay? We saw the COOH. That is indicative of, that's just the formula part of the end. Okay? And you saw that a lot. Hopefully you recognize that. Okay? It is only ever that H that comes off. Please don't try to remove any of the other H's. Naming rules. We're going to drop that E again from the alkane stem, and we're going to add oic space acid. It's the first space we're going to have in a name. So a 3-carbon long carboxylic acid. These will be future examples that'll do. we need to start with the stem. There's no branches here. That's the stem. Occasionally students will rush and they'll miss this carbon for some reason, or a common error is a student looks and only counts 2, particularly when the chain gets long, like a decanoic acid. Just for some reason, student size, not often, but you'll just miss that one. So just be careful if you're counting. So this is propane. Okay. I have dropped the E, I didn't even write it. And now I have to add oic acid. OIC is stuck to that first word, space, acid. No, it's just me being lazy, and I should have, in a full structural formula, I should have dashed it out. When I'm just writing, if you're just asked to draw, that's okay. I've condensed that in a little bit. But technically, if you ask for a structural formula, you should dash everything out. I'm kind of doing whatever format I want. Now, do I need a number? Should this be propane 1 oic acid? To help answer that question, I'm going to move it to the middle just to see if that could happen. So 1, 2, 3 carbons. This is what the 2 version would look like. Could that happen? No. Yeah, too many bonds. If you try to put it anywhere in the middle, 1, 2, 3, 4, 5, you're just making up science now. This doesn't happen. Okay, there's only 4 orbitals. We learned, 1 s and 3 p's. This just isn't possible. So this is out. You never need a number. There is no way you can have a carboxylic acid and not have this functional group on an end. It could be over there, but it would still be the 1 position. It happens to be here, it's in the 1 position. You never ever put a number in here. It's never needed. You might need some numbers for the side groups, but you'll never need a number there. You won't see it. Second bullet is another one of those. Benzoic acid is a building block, a molecule used for tons of pharmaceuticals. And its structure is so important it gets a name. Maybe someday someone in here will come up with a building block molecule that's so fundamental to science, you'll get to name it. Okay? Benzoic acid is one of those molecules. So you're seeing that kind of benzene name there. So there is a aromatic ring, one of those benzene rings in benzoic acid. I'm going to use the line structure. I can put the C double bond OH right on the ring. There's nowhere near enough bonding capacity for that. So it sits 1 carbon off. I dashed it out that time because I could just remember the comment I got about sticking it together. And that is benzoic acid. Now the carboxyl functional group could be there or there or there. It doesn't matter. It's in the 1 position no matter what. And we're going to do a lab, and at least 1 group is going to have benzoic acid on their lab bench. So this is a chemical we will use in this course. The painkiller ASA has this structure as the heart of acetylsalicylic acid. Salicylic acid is just a slight variation of benzoic acid. Last example for this first lesson of today, 3-chloropropanoic acid. Do I have to put the C? It's there if you're doing, I kind of mixed. I did a line structure here and a structural formula there, which you actually see line structures used all the time for benzene rings, but I did sort of a structural diagram up here, so I had to put the C in. I could do a whole total line structure of this. So this is a mix, line on the bottom, structural on the top. And the textbook, the diploma writers, and so myself, do this mixed structure a lot with the benzene ring, because this is just such a nice way to show the ring. Okay? Realize the H's have been all dropped on those corners, and there's no carbons, but this will be full line. So I've got a carbon there. I'm going to go 0, because I'm already on a carbon. 1, lift. There's my carbon. Off of this carbon is a double bonded O. I have to put an O here, because you have to write letters other than C and H. I've got a dash there to an O, so I have to dash out, put an O, and then I have an H. Normally we leave H's out, but not when they're connected to a letter that isn't carbon. So that's a full line structure for benzoic acid, where that's a mixed. Three-chloropropanoic acid, prop, 1, 2, 3. Oic acid, C double bond OOH, doesn't matter what side. I tend to go on this side a lot. I'll go to this side. I'll do a full structural diagram. So I dashed out my H properly. And this is where I have to number from. This is my 1 carbon, my 2, my 3. Okay, that sets my numbering. Okay. 3-chloro, so that's very clear that that's where my chlorine is going to go on the end. Do watch out, don't put H's here. All 4 bonds are used up. That's another common error I see. I've done it. Sometimes you rush and I'm putting all these H's on the bottom and I stick one in there and I shouldn't. So 2 more families done. We're almost done our families, which is why we're going into reactions. The one family that we're going to do next, or last family, won't be next because the family comes from a reaction. If you take an alcohol from today and a carboxylic acid from today, you can make an ester. So we're going to go through our reactions, we'll learn about esterification, and then we'll talk about that new family at the end of that reaction section.